Alright guys, this is your review for your test tomorrow. Basically a review of what we've been doing the last 2 weeks. You can use this review on your test. So, first section there on the first page, first 4 says use finite differences to determine the degree of the polynomial that best describes the data. So what you're doing here is you're subtracting y values and seeing where you get a constant difference. Alright, so if you look at the first one, you can start, I would really just start down here at the bottom with 114. I'd go 114 minus 150 and write that number down. You get negative 36. 150 minus 178, get negative 28. 178 minus 186 gives you negative 8. 186 minus 164 is 22. 164 minus 104 is 60, and then 104 minus 0 is 104. So obviously the first differences aren't the same, so let's go to the second. We got negative 36 minus negative 28. That results in negative 8. We got negative 28 minus negative 8. That becomes negative 20. We got negative 8 minus 22. That's negative 30. And we got 22 minus 60. And that's negative 38. And then 60 minus 104 is negative 44. Those aren't the same. Go to the next set. Negative 8 minus negative 20 is 12. Negative 20 minus negative 30 is 10. Negative 30 minus negative 38 is 8. And then negative 38 minus negative 44 is 6. Those don't match, but you can probably see what's going to happen. You go to the next one. 12 minus 10 is 2. 10 minus 8 is 2. 8 minus 6 is 2. So the fourth set of differences match. So the degree here is the fourth degree, which is a quartic polynomial. So the degree is the fourth degree. Biggest thing, guys, is when you're subtracting all these negatives, make sure you punch the stuff in right. Like this one right here would be negative 8 minus negative 20. You would type it in like this, negative 8 minus negative 20. If you don't type it in like that, it's not going to be done right. Alright, look at number 2. Got the same thing. We're looking at differences here. Okay, I would, again, start at the bottom. Negative 95 minus negative 67 makes negative 28. Negative 67 minus negative 42 makes negative 25. Negative 42 minus negative 20 makes negative 22. Negative 20 minus negative 1 makes negative 19. Negative 1 minus 15 makes negative 16. And 15 minus 28 makes negative 13. Okay. Then we go to the next set. We got negative 28 minus negative 25. That makes negative 3. Negative 25 minus negative 22 makes negative 3. Negative 22 minus negative 19 makes negative 3. Negative 19 minus negative 16 makes negative 3. And negative 16 minus negative 13 makes negative 3. So this time it's at the second differences. So you have a quadratic polynomial because the second degree or the second differences are the same. Alright, go down here to 3 and 4. Doing the same thing. We're subtracting. Okay, start at the bottom. Got 455 minus 352 makes 103. 352 minus 274 makes 78. 274 minus 211 is 63. 211 minus 153 is 58. 153 minus 90 is 63. And 90 minus 12 is 78. Okay, those obviously don't match. Go to the second ones. 103 minus 78 is 25. 78 minus 63 is 15. 63 minus 58 is 5. 58 minus 63 is negative 5. And 63 minus 78 is negative 15. Those don't match either. Go to the third set. 25 minus 15 is 10. 15 minus 5 is 10. 5 minus negative 5 is 10. And negative 5 minus negative 15 is 10. So this time the third set of differences are the same. Therefore, you have a cubic function or a third degree function. So the biggest thing, guys, is, practice punching this stuff in. Okay? Don't just write down what I'm saying right here. Practice punching in. Hit pause. Punch it in. The last one, doing the same thing. This one has a lot of negatives, so this is where you got to really be on your P's and Q's about what you're typing in. For instance, negative 490 minus negative 460 is what should be typed first. Gives you negative 30. And I got negative 460 minus negative 420, which gives me negative 40. And negative 420 minus negative 364 gives me negative 56. Negative 364 minus negative 290 gives me negative 74. Negative 290 minus negative 200 gives me negative 90. And negative 200 minus negative 100 gives me negative 100. Obviously, those don't match, so I would go to the second set. All right, so we're subtracting the second set. Negative 30 minus negative 40 is 10. Negative 40 minus negative 56 is 16. Negative 56 minus negative 74 is 18. Negative 74 minus negative 90 is 16. And then negative 90 minus negative 100 is 10. Alright, so again, those don't match. Go to the next set. You got 10 minus 16, that's negative 6. 16 minus 18 is negative 2. 18 minus 16 is positive 2. And 16 minus 10 is 6. Again, they don't match. Okay, make sure you don't choose these, even though you see the negatives. Negative 6, negative 2, 2, 6. Not the same numbers. So do it one more time. You got negative 6 minus negative 2, that's negative 4. Negative 2 minus 2 is negative 4, and 2 minus 6 is negative 4. So just like the first one, the fourth set of differences, or a quartic function, are where you have your constant. Quartic function is a fourth degree function. All right, let's move on to number 5. Now, number 5 is kind of tough. You've had this one before. Population of a rare species of turtle on an island for the years since 1980. So, first thing you need to do is look at the years and convert them into x values. So 1980 would be year 0. That's where you start. 84 is 4 years later. 88 is 8 years later. Let's see. 1990 would be 10 years later. 95 would be 15 years later. 2000 would be 20 years later. 2001 would be 21 years later. And 2005 would be 25 years later. Now, here's the thing. Okay, the x values don't go up by the same number each time. So what we have to do for this is what we did yesterday. We have to put the data in, choose some different regression functions, and see which one has the highest correlation coefficient, or the r-squared value. So before you get into this, you want to make sure r-squared shows up. You hit second 0 and scroll down till you see diagnostic on. O-N. And it's in alphabetical order, so you should go all the way down. D-I-A-G-N-O-S-T-I-C, on. Click enter, enter, and it'll say done. And that means that when you show your regression equation, you'll be able to see what r-squared is. So let's put the data in, and I'm going to project the steps for the data on your test tomorrow, okay? But the first thing you would press is stat and then enter. We're going to put the numbers we change the years to in for the x's. So we're going to put 0, 4, 8, 10, 15, 20, 21, 25. And then we're going to go and put the population values in y. So we're going to put 1,000, 736, 1208, 1600, 2650, 3200, 3184, and 2500. So just check your table right now to make sure that everything matches exactly as you see on your paper. All right. Now, again, like I said, the x values, they don't go up by the same number every time. So we have to see which one of our regression equations will work. Well, let's do what we did yesterday. Let's do quadratic, cubic, and exponential. So we got quad, cube, exponential. And all I'm going to write down first for all these is their r-squared value. So to figure out that regression, I'm going to hit stat, go right to calc. For quadratic, I'm going to go down to number 5, quad reg. Scroll down to calculate, hit enter. All right, and its r-squared value is 0.8100 blah blah blah. Okay, 0.81, not very close. All right, let's go to cubic. So for cubic, I'm going to do the same thing. I'm going to hit stat, go over to calc, go down to cubic, go down to calculate, and let's see, the cubic one, r-squared, is actually equal to 1. It's exactly 1, so quadratic's out. I'm going to bet that exponential's probably out too. Let's just make sure. So we'll go to stat, go over to calc, down to exponential, go down to calculate, and exponential's r-squared value is 0.8 something. So that one's out. So cubic is the one we want. So let's go get that equation again so we can write the polynomial function up here. So stat, over to calc, down to cubic, down to calculate. All right, and the function looks like this. Y equals, it says a is -1, so you got -1, x to the third. Plus, b is 35, so 35, x to the second. C is -190, so minus 190, x. And d is 1,000, so plus 1,000. Okay, that's your equation. Now the question is, predict when the species will become extinct. So when, we want the year when the population equals 0. Well, here's the thing. The population is the y value. So if the y value is equal to 0, what you're technically looking for is the x-intercept. Okay? That will be the year when the y value is worth 0. So we got to graph this equation. You can use the vars key, or you can just go to y equals and type in this equation that you wrote down for a. -1, x to the third, plus 35, x to the second. And again, I'm typing this in y1, minus 190x, plus 1,000. Now you're going to have to change your window. So if you go to window on this one, look at the years. The years go from 0 to 25, okay? But at year 25, there's still 2,500 turtles. We want to know the year, so it's going to be past 25 years when there's 0 turtles. So my window here, I would make my x minimum 0. I'd make my x maximum something like 45, just to give myself some room. Okay. Leave the x scale, x SCL, as 1. I do my y minimum because my y's are my years, and I'm trying to find my x-intercept. Okay, so let's make our y minimum 0 because that's what we're looking for is when the graph touches the y-axis. Now let's make our y maximum because the population goes up all the way to 3,200. Let's make it 3,300. Okay, so go ahead and change your windows. Once you get these changed, hit graph, and you're going to see it draw a graph. It's going to come down, and you can see it touch the x-axis. That's what you're looking for, because when will the species become extinct? When the graph hits the x-axis, there are 0 in the population. So hit the trace button, use the cursor, and scroll down there. Now, probably when you get really close, you get x is 29.69 and y is 34. Okay, so the population's at 34. And if you look, the x value is really right around 30. I mean, 29.6, that's right around 30. So if the x value equals 30, you have to go 30 years after the beginning, which was 1980. So x is 30, add 1980 to that, and you get the year 2010. So that's the prediction for when they will become extinct. The x-intercept is 30 years after the start. Well, 30 years after 1980 would be 2010. Okay, and again, the word predict. It's not exact because, again, I'm on x is 29.6 and y is 34.3. So the y value is not technically down to 0 yet, but it doesn't have far to go down, and the x's aren't moving very far to the right. Okay? All right, let's go to the next example. Determine whether f is an exponential function. If so, find the constant ratio. So for exponentials, you have to divide. Okay? Instead of subtracting, you would divide. So for this one, we would take 32.8 right here and divide 22.8. Let's see, we get 1.43. Now we get a bunch more, but 1.43. Okay? Then we go 22.8 divided by 14.8, and we get about 1.5. All right, and then we go, did I do that? Let me make sure I did that right. 32.8 divided by 22.8. Okay, then we go 14.8 divided by 8.4, and we get 1.76. And then we got 8.4 divided by 3.28, and we get 2.56. So for this one, I would say no. Number one. Okay? Our ratios are not the same. Go to the next one. 28 divided by 21 is 1.3 whatever, repeating. 21 divided by 14 is 1.5. 14 divided by 7 is 2. And 7 divided by 3.5 is 2. So that one again is a no. Okay. Look at the next one. We got 27 over 2 divided by 9. And that's 3 over 2, which 3 over 2 is 1.5. 9 divided by 6, 1.5. 6 divided by 4, 1.5. And 4 divided by 8 over 3 is 3 over 2, which is 1.5. So number 3 is a yes. And the common ratio is 1.5, or 3 over 2. Okay, you look at the next one. You go 12 divided by 18. You get 0.6 repeating. 18 divided by 27, you get the same thing, 0.6 repeating. It's got that 7 at the end. 27 divided by 81 over 2. Let's see, it becomes 2/3, which is the same thing, 0.6 repeating. And then you've got 81 over 2 divided by 243 over 4. And you get 2/3 again. If you want to convert that to a decimal, you can hit math, go down to DEC, hit enter again. And it's the same thing, 0.6 repeating. So this one is, again, yes. And the ratio is 0.6 repeating, or you could have written 2 over 3. Either one of those would work right there. Okay. Let me check one more time the first one. 32.8 divided by 22.8. 1.43, 22.8 divided by 14.8. Yeah, the first one's not. Okay, so it's no, no, yes, yes. All right, let's move to the next page, or the next set. We're going to use exponential regression to find a function that models this data. So it tells us to use exponential. So we start with stat, hit enter, and we're going to plug in our data. You're going to plug 1, 2, 3, 4, and 5 in for x, and then you're going to plug those decimals in for y, 9.3, 21.8, 50.8, 118.6, and 276.6. Again, it told us to do exponential. After you plug them in, you'll hit stat, go over to calc. Exponential regression is down at 0, so you hit enter down there, go to calculate, hit enter. All right. Now, the a value in this function is 3.99, so I'm going to write this as y equals 4 times the b value is 2.33, so I'm going to put 2.3 to the power of x. You could have also written 4 parentheses 2.3 to the x. Either one of those is right. All right, do the second one. You do the same thing. You hit stat enter. Put your x and y values in. 2, 4, 6, 8, 10. And then your 413.2, 45.5, 4.9, 0.6, 0.1. Once you've got all that in, you go stat over to calc, and again, go down to exponential regression. Go down to calculate. It should give you a function. All right. The a value this time is about 3035. The b value is about 0.4 or 0.35, however you want to write it, to the power of x. You could have also written it as 3035 times 0.35 to the x. It's kind of what it looks like in the calculator. Either one of those would work. All right, 7 and 8 say use logarithmic regression. Starts out by putting the data in the same way. You hit stat enter. All right, first one, put our 1, 2, 3, 4, 5 in. We got -4, -3.7, -3.5, -3.3, -3.2. Hit stat, go over to calc. And this time we're going to natural log regression or logarithmic. You choose number 9, which is LN regression. Go down to calculate. All right, and it brings up an a value and a b value. For this one, the a value is about -4, so you write y equals -4 plus the b value is about 0.5, so plus 0.5 times the natural log of x. Okay, that's how you would write that. You go to number 8, we're going to do the same thing. We'll hit stat, hit enter, delete out your L1, L2. Put your L1 in, 2, 4, 6, 8, 10, 1.5, 1.7, 0.5, 0.4. Okay. We go stat over to calc, and we go natural log regression. Down to calculate. And this time, the a value is 1.97, so we got y equals 1.97. The b value is negative, so we can write minus, and it's 0.697, so we'd write minus 0.7 times the natural log of x. Okay, I can put minus right there because the b value is negative. All right, number 9. Number 9 says use exponential regression. So again, stat enter. It ought to be becoming second nature. Put 1, 3, 6, 8, 10 in for the x's. And put your bacteria number in for the y's. 413, 575, 945, 1316, 1832. Okay, then go stat, go over to calc, and we're going to exponential regression because that's what it tells us. That's done at 0, hit enter, go down to calc, hit enter. So the first thing we need to do is write down the function. Well, the a value is about 350, so we got y equals 350 times. The b value is about 1.18. So 1.18 to a power of x. Now, the question is, when will the number of bacteria reach 2,500? Now, bacteria are the y value, so I want to know the time when the y's equal 2,500. So we're going to go graph this here in a moment. We're going to put the original equation in for y1, and we're going to put this y equals 2,500 in for y2, and find the point where they meet, the x value where they meet. So let's go back to y equals, and you can do the vars, you can go vars down to statistics, over to EQ, and put your regression equation in. Or what I'm going to do is I'm just going to type in what we've got. So in y1, I'm going to put 350 parentheses 1.8 to 1.18 to a power of x. And then in y2, I'm going to put 2,500. Now, I might have to change the parameters of my window. I think we're going to be okay. Let's just hit graph and see if we can see where they touch. If not, we might have to change them. All right. So if you left your window the same as we did on the one before, you're fine. You can see the red and the blue lines there. So hit trace, and let's take our cursor and see how close we can get it. Somewhere between 11 and 12, the x value is somewhere right in between 11 and 12. If you want to write anything from 11 to 12 minutes is fine right here. Okay, I may put I'll just put 11.5 minutes. But if you look at the cursor there, it's right in between 11 and 12, somewhere in there. Now the next question is, how many bacteria will exist after 1 hour? Well, 1 hour is 60 minutes. 60 minutes, and minutes are the x values. So to figure that out, you take the original equation, 350 times 1.18 to the x, and instead of x, you put a 60 in there, and you put it in your calculator, and you calculate it out. So go back to your home screen, and you type in 350 times 1.18 to the power of 60, and it gives you 7,194,299 if you're rounding. 7,194,299 bacteria. All right, let's go to the last page. All right. This one says to use constant differences or ratios to determine which parent function would best model the given data set. All right, and you don't have much room here, so I'm going to write it down below. I would try the division first because you can see it immediately after 2 times because it should work the first time. So if we do the first one with division, we'd put negative 0.2 divided by negative 0.2, and we get 1. And then we'd go negative 0.2 divided by 0.2, and we get negative 1. It's not the same number. 0.2 divided by 1 is 0.2. It's not the same number. So this one's not exponential. All right, so let's subtract. Negative 0.2 minus negative 0.2 is 0. So this first subtraction is 0. Negative 0.2 minus 0.2 is negative 0.4. Okay, and then I have 0.2 minus 1, which is negative 0.8, and then 1 minus 2.2, which is negative 1.2. Don't match, but I'm going to subtract again. 0 minus negative 0.4 is 0.4. Negative 0.4 minus negative 0.8 is 0.4. And negative 0.8 minus negative 1.2 is 0.4. So the second difference is they work. This is quadratic. Just like I did on that first one, on this one I'm going to try the division first. 4.05 divided by 27.15. 27 divided by 180, 0.15. 180 divided by 1200, 0.15. And 1200 divided by 8000, 0.15. So when I divide, I got the same number, so this is exponential. An exponential model would be best for that scenario. All right. Now we did that to lead into these next 6, but now listen, we're not going to do 5 and 6. Do not do number 5 and 6. Okay. So looking at number 3, I look at the x values. Negative 7 to negative 4, that's up 3. Negative 4 to negative 1, that's up 3. Negative 1 to 2 is up 3. 2 to 5 is up 3. So I want to figure out if there's any relationship between the y values. And if I look at them, they go from really big to really small in a hurry. So I'm going to try dividing them first to see if it's exponential. So 0.125 divided by 1, that's 0.125. 1 divided by 8 is 0.125. 8 divided by 64 is 0.125, and 64 divided by 512 is 0.125. So for this one, for number 3, I want to use exponential. Okay, so I'm going to go stat, enter, clear my L1 and L2, and I'm going to plug in the data. Negative 7, negative 4, negative 1, 2, 5. 512, 64, 8, 1.125. Okay? And I'm going to go stat over to calc, and I know this is exponential, so go down to 0, exponential, down to calculate, hit enter. And my A value is exactly 4. My B value is exactly 0.5 to the power of x. And if you look at the r squared there, it's exactly 1. So this data fits exactly on an exponential. Okay. Now you look at the next one, and they don't look to be multiples. So let's subtract. Negative 2.5 minus negative 0.1, that's negative 2.4. And then negative 0.1 minus 2.3, that's negative 2.4 again. Then 2.3 minus 4.7 is negative 2.4, and then 4.7 minus 7.1 is negative 2.4. So this one is a linear because the first differences are constant. Okay? So again, I go stat, enter, and I'm going to punch my data in. You got negative 6, negative 3, 0, 3, 6. Then you got 7.1, 4.7, 2.3, negative 0.1, negative 2.5. Stat over to calc, and this is linear regression, so I'm going to choose number 4, go down to calculate, hit enter, and my equation is negative 0.8x, because that's A, plus 2.3. Again, my r squared value is 1, so that data fits very well. Okay. Looking down at 7 and 8, as I look at number 7, the numbers change drastically again, so I'm going to try my division first. 45.17 divided by 79.81, is 0.565. 79.81 divided by 141 is roughly the same thing, 0.566. 141 divided by 249.11 is 0.566. And then 249.11 divided by 440.11 is about the same thing. So this one is exponential. So let's put our data in and find an exponential. So stat, enter. Delete stuff out of L1 and L2. And we'll put in our 0.4, our 0.7, 1, 1.3, 1.6. And then we got 440.11. 249.11, 141, 79.81, and 45.17. Okay. So we plug that data in, and then we go stat over to calc, and we know we're going down to exponential. And this one's going to be more of an estimate. Okay. So I'm going to have y equals, the a value here is about 940. The b value is about 0.15 to the power of x. All right, looking at number 8, I'm going to start with subtraction here. Okay, 0.15 minus 0.65 is negative 0.5. 0.65 minus 0.83 is negative 0.18. 0.83 minus 0.69 is 0.14, and then 0.69 minus 0.23 is 0.46. Those don't match, but I'm going to go to the second set. Negative 0.5 minus negative 0.18 is negative 0.32. Negative 0.18 minus 0.14 is negative 0.32. And then 0.14 minus 0.46 is negative 0.32. So this one is a quadratic. So when we put the data in, we've got to do quadratic regression. So we hit stat, enter, and delete out the data from the previous one. We're going to put this in, negative 0.6, negative 0.2, 0.2, 0.6, 1. All right, and we got 0.23, 0.69, 0.83, 0.65, 0.15. All right, and we'll hit stat, go over to calc, and this one is quadratic, so we're going down to number 5, going down to calculate, hit enter, and this r squared is exactly perfect, so the equation is y equals negative 1 x squared, you could have just written negative x squared, plus 0.35 x plus 0.8. Negative x squared plus 0.35x plus 0.8. All right, our last problem. The table shows the number of shares of stock listed at the New York Stock Exchange since 1950. All right, the first thing is to write a function that models the data. Now, if you look, the x's go up by 10 every time, so try figuring something out down here at the bottom. Look at the numbers at the bottom. They go from 2 to 6 to 16 to 33 to 90 to 313. I would start by trying to divide. So 313 divided by, 313.9 divided by 90.7 is about 3.48. 3.46. 90.7 divided by 33.7 is about 2.69. 33.7 divided by 16.1, 2.09. 16.1 divided by 6.5, 2.47. And 6.5 divided by 2.4 is 2.79. So it really went from the mid threes to the to the low twos actually. So I'm not sure if it's exponential yet. It could be, right? Because remember, this is real life data. If you subtract though, it's going to take a little bit to a few sets of subtraction to get remotely close. Let's do what we did yesterday, and let's make three functions. One that's quadratic, one that's cubic, and one that's exponential, and look at the r-squared values. Okay, we use the same data. So go to Stat, Enter. We'll delete out what we have in there so far. All right, and we got our years are 1, 11, 21, 31, 41, 51, and our numbers are 2.4, 6.5, 16.1, 33.7, 90.7, and then 313.9. The thing that makes me think it's exponential is this ginormous jump right here from 90 to 313. Exponential means really fast growth or decay, and that's really fast. It starts small, 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 and then all of a sudden, bang, it grows. So I got the data in there, so let's go Stat over to Calc, and let's try quadratic first. Go to Quadratic Regression, down to Calculate, and let's see, its r-squared value for quadratic is 0.9303. 0.9303. If we have to look at it again, we will. All right, then we're going to go Stat over to Calc, down to Cubic, which is number 6, down to Calculate. Look at its r-squared value. It is 0.992139. 0.992139. So quadratic is out. So go Stat over to Calc, and let's go down to exponential this time. And let's see, its r-squared value is 0.997. 0.997, so that means cubic is out. We want to write down this exponential. So this exponential would be y equals, A is about 2.15, B is about 1.1, and that's to the power of x. So that's your function. So the next thing is use your model to predict the number of shares that will be listed in 2010. Well, you got to figure out how many years 2010 is after 1949. 1 year right here would be 1950. And this would be 60, 70, 1980, 1990, 2000. So 10 years later will be 2010, where the x value is 61. So to make this prediction, you have to take the equation you just wrote down, 2.15 times 1.1, and you got to put a 61 in for x and see what you get. So 2.15 times 1.1 to the power of 61, and it's roughly 720.1 billion. Okay, because these numbers, the shares, the y values are in billions, so you can add billion to that. Okay. And then it says, use your model to determine the year in which the number of shares of stock listed first exceeded 10 billion. All right. So this is where we want to graph this. So we go y equals. And in y1, we want to put our function 2.15 times 1.1 to a power of x. Now, your shares exceeded 10 billion. Your shares are the y values. So you want y2 to equal 10. So y2 is going to equal 10. I would change my window now. I would go window, x is from 0 to, let's just go from 0 to 51. And my y's go from 0 up to, let's say, 400. And then let's graph it. We're going to find out where those two lines meet. You know what, to go back and change that window. Instead of 0 to 400, the y max, let's make the y maximum 20, because we only want to go up 10 spots. It'll make it easier to see. All right, so we can see these two things crossing here. So what we're looking for is the x value where they intersect. All right, so hit trace. Bring your cursor back. Try to get it as close as you can. Really, it's about 16.2. Okay, so 16 years, let's see, somewhere in between 15 and 16 years. So it's a little over 16 years. So it's about 1965. Because you want to know where it goes over 10 billion. So x equals about 16. So you started in 1949. So you would add 1949 to that, and you get 1965. That's about the year when you exceed 10 billion. Okay. If you got any questions, make sure you ask. You will have a test tomorrow, and you will be able to use this.